All right, hey guys, Mr. Fortin here. I know that in class today we started this assignment, which was the chapter 6 kind of section 6.1 to 6.4 type of review, right? Pre-trigonometry, right? Triangles questions that we had. Still makes me laugh here. I know that some groups didn't get as far as they kind of wanted to. Some groups finished. So I said that, hey, you can give the rest of these problems a shot, and then I can film a video kind of explaining them. Now, you probably also noticed, too, that these questions appear in your problem set that's due Wednesday. So you do have a homework, just kind of review. It's your opportunity to review chapter 6. This is what's due on Wednesday, technically. I'm also going to show you what's due Thursday as well, too, with today's assignment. But anyways, what's due on Wednesday, if you haven't done it yet already, is the chapter test here. Again, it's just practice. There's a chapter review. I think it's chapter the test here. So kind of an example test here. So hopefully stuff like this on Friday relatively close to this. I don't know. I try to make sure that there are some challenging questions here and there, and everybody should feel a little challenged at least by an assessment, so you can see really how you're doing. If nobody's challenged by it, then it's not really an assessment, right? Like, I don't see how I'm doing. So, anyways, if you check it out here, this question's in it. Like, this one's in the little Desmos thing that we had the other day. I think a lot of them are on it. So, anyways. You'll get these answers on the Jamboard on Wednesday, but perhaps I can go through them right now in case you're curious. So anyways, check out this one. Almost everybody got this one right here. So this one was 10. Geometric mean, of course. A mean is an average, right? An average here. So 5 to 10 is the same as 10 to 20, right? They're both 1 to 2 ratio. So anyways, you can logic through it like that, but it might just be easier just using this formula here. 5 to x equals x over 20, right? Cross multiply, you get x squared. Is equal to 100, and then you can't. A few people mistakenly put 100 in class earlier today. You have to take the square root of both sides to get 10 as your answer here. I'd include this. This is the formula I'd use for geometric mean from now on. Like here, remember geometric mean is it's a number that occupies both the mean positions between the two different numbers. These are the means, these are the extremes. But if you're cross multiplying and then cross multiplying this, you're gonna have to take the square root at some point. So this is just a shortcut to do it. Let's maybe do the shortcut on this one here. The geometric mean of this one here would be x equal to root. This is messy. Man, this Desmos here. I gotta kick myself if I'm doing it. Square root is what I'm trying to do here. Symbol of 6 times by 8. And so some people are putting in their answers as root 48, because 6 times 8 is 48, right? But that's not fully simplified, okay? So by now, you should have practiced simplifying square roots, which was several Wednesdays ago. We had a lesson on that. Where I just attached some YouTube videos from some masters who have hundreds of thousands of views explaining how to simplify square roots. So if you watch those videos, if you did the practice little worksheet that we did, simplifying square root of 48 isn't super complicated, okay? So what you could do is you could figure out, well, does 2 go into 48? Yeah, it does. It goes into 48 24 times. Does 2 go into 24? Yeah, it does. It goes into it 12 times. So I know 2 times 2 times 12 would bring me to 48. I could pull a 2 on the outside, and then it would be 2 root 12. But then again, remember, does 2 go into 12? Yes, it does. 2 times 6 is 12. Does 2 go into 6? Yeah, 2 does go into it as well. So I can pull another 2 out. So I'd have 2 times 2 root 3. Anyways, a faster way to potentially do this one is to think, what are perfect squares, right? Perfect squares, you should maybe heard this term before. Perfect squares are stuff like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. 5 squared is 25. Why am I saying that? Well, is there a perfect square that goes into 48 that's perhaps a little bit bigger than 4, right? 4 goes into 48 12 times, but 4 also goes into 12. So what's 4 times 4? That's what I'm getting at here. Does 16, right? 16 is a perfect square. Does that go into 48? Yeah, it does, right? Square root of 16 times by 3 would be a way we can write 48 in terms of its factors, okay? 48 isn't a prime number, it's a composite number. So we can find some factors here, one of which is a perfect square, right? 16 times 3 is 48, so the square root of 16 times 3 is the same thing as square root of 48. So I can take the square root of the 16 right here, and I get 4. So I get 4 root 3 would be my answer to this one here. And the Desmos is really slow. 4 root 3 is my answer. It looks like it's 1 right here. I don't want that. I want the 4 root 3. Okay, so I'm going to go ahead and put that in as my answer here. 4 root 3. Okay, you have to do roots on the quiz too, so you have to know how to get your roots on Desmos here. You got to click that button. There we go. Little keyboard, and then it'll do that. Okay, and there are my answers here for both these. Okay, most people got that right. Not everybody got that right in today's class, but moving onward, we have this one here. Square root of 48. Hey, we just did that a second ago, so we spent the time doing it. I can type it in and get my answer. So 4 root 3. Okay, root 3 is a prime number, right? So I can't take the square root of root 3 because nothing multiplies. I think it's 1 and 3, right? In terms of integers or whole numbers would go into 3. So anyways, there's no perfect squares that go into 3 for sure. 1 doesn't go into 3. 4 is bigger than 3, right? 16, 9, 25, I don't care. So anyways, so 7 is a prime number too. We don't have to worry about simplifying that. Also, there's no square root there. Square root of 2, that's a prime number. We don't have to worry about simplifying that. But wait a second, this is called rationalizing the denominator. Check it out. So these are the 2 things you need to do. This is just sort of a reminder here. Let's get this out of the way of the 2 things you need to consider when simplifying a square root. Okay, so again, this was in that lesson several Wednesdays ago, right? We had this one before we started chapter 6. We're like, all right, we're gonna have to do this. Right? They were like literally like 3-minute, 4-minute videos that I posted. One for this one for this one to get the juices flowing. Did you watch those videos? Right? Does this ring a bell at all? Okay, rationalizing denominators. Here's an example. If I have 12 over root 3, what I do to rationalize the denominator is that you find whatever is that irrational number, right? Square root of 3, okay, is kind of a made-up number, right? We need to find numbers that multiply themselves to become 3, and it turns out there's just a kind of a decimal approximation of that here. So square root of 3, if I do that on a calculator, there's no pattern to it. It's non-repeating, non-terminating here. So it's something called an irrational number, square root of 3, okay? So you can't divide by something like this because it keeps going on forever. And this will be something you study in algebra 2, but and beyond, right? But anyways, so the rule is you can't have a square root in the denominator. That's it. I'll make it a rule for it. You can't have a square root in the denominator. So if you can't simplify square root of 3 because it's not a perfect square, you need to get rid of it somehow. Here's how you do it. You multiply it by 1. Right, multiply by 1. So did you know that you can, if you have a certain quantity, a certain amount, like say the number 5, and you multiplied it by 1, did you change that quantity? No, you didn't. 1 times by anything leaves that thing the same. It's called actually the identity property of multiplication. Property we don't really emphasize too much, but should make total sense to you. So if I have 12 over root 3, okay, and I multiply the numerator and denominator by both root 3 right here, I do something called rationalize the denominator. Why? Because when you're multiplying fractions, the rule is to multiply numerators together. So 12 times root 3 would be 12 root 3. That's fine. I got a root 3 in the numerator. That's fine. I didn't say you can't do that. You can't have a root in the denominator. The denominator will be root 3 times root 3. What do we know about that? Well, any root times itself, times the same root itself, will become that number, right? It'll become that number. That's just how roots work. They're the 2 numbers. That's representative of the number that when multiplied to itself, and there it is to itself, becomes 3, right? That's the definition of the square root of 3. So this becomes 3 here. So here we've rationalized the denominator here. It was root 3. We just simply multiply by root 3 over root 3, which is 1. We're allowed to do that by the identity property of multiplication. And then the denominator, boom, radical symbol gone, is here. But the thing is, we have 12 root 3's in the numerator, and we've split that 3's ways, right? We have 12 root 3's in the numerator, and we're saying, what this statement here is saying is that divide those 3 ways. We'll apply 12 root 3's, and I'm dividing those 3 ways. Then each person is going to get 4 root 3's, right? You treat root 3 kind of like a variable, right? So picture this as like 12x divided by 3, right? 12x divided by 3, so that would be, it's 4x's. Same thing here too. Everybody gets 4 root 3's, and you're good to go. So the last step is, right, that number, the coefficient here, would get divided by whatever in the denominator, right? That's what a fraction bar is, it divides. So in this one here, some people were getting this one incorrectly in the when I was checking out your guys' classwork today. So anyways, this one would be 7, right? 7. I don't know if I have time to do all of these, do I? Okay, 7. You'll get the answers too on the Jamboard on, can't do it. Anyways, multiply by root 2 over root 2, and then you would get 7 root 2 over 2, and there's your answer. Okay, so this is 7 root 2 over 2. This one here, you're gonna have to do this one here too as well. So people weren't really sure what to do. This whole thing, 5 over 8, the whole thing's underneath the square root symbol. So what does that mean? Well, right? There's just a lot of rules in math. There are. So what you're trying to learn before you get to the kind of really the advanced stuff here is that this is equivalent to square root of 5 over square root of 8. And this is just really struggling. I think my computer is going pretty slow because I'm uploading my lesson video for section 6, 7. Anyways, this one here, what you do here, you still have to get rid of that square root of 8 here, okay? So in this one here, right, we can't have that square root of 8. We'll multiply by square root of 8 over square root of 8, okay? This is driving me crazy. So I'm going to stop typing and writing on this because it's not working here. Multiply by square root of 8 over square root of 8. I would get square root of 40 here. So remember, you can multiply square roots to one another. That's totally legit, totally allowed. Okay, multiplication generally is pretty favorable. Like if you can multiply with square roots, because square roots has to do with multiplication. So if you multiply together, we can generally do that. So square root of 5 times square root of 8, square root of 40. So you'd have square root of 40 over 8, right? Not square root of 8 anymore. Anyway, square root of 40 over 8. And then you could simplify square root of 40, right? Because 4 goes into square root of 40, and 4 is a perfect square. So 4 times 10, square root of 4 times 10. So 2 root 10 all over 8, and then 2 over 8 reduces to 1 over 4. Anyways, the answer to this one is root 10 over 4. That's the answer. That's just me, if you have questions. Okay, this one here, we don't have to rationalize the denominator. That one's nice. But here, square root of 20, 4 goes into 20. How many times does it go into 20? It goes 25 times. So 4 times 5 is the way we change it. Can we take the square root of either of those numbers, 4 or 5? We can. Square root of 4 is 2. So this would be 3 times by 2 times by the square root of 5. So that would be 6 root 5. Oh, wait, 6 over 4. Can I reduce that fraction? Yes. So 3 root 5 over 2 would be the answer. 3 root 5 over 2. Okay, so anyways, hopefully that helps here. All right, let's keep going. Maybe emphasis should be on speed rather than actually showing you because my computer is being very slow. All right, let's check this one out here. Here we have a right triangle. Okay, so here, fill in the blank here. This is a right triangle. So we have a right triangle. Describe a situation at right, filling in the blanks. This is a geometric mean geometry tattoo. So you should remember this situation where this comes into play. If I have a right triangle and I draw in the altitude, here we have an altitude drawn, okay, to its hypotenuse, okay? So this is the whole situation. If you look at, right, we have kind of the theorem right down here, okay? If we have a right triangle here, right triangle DNF, and an altitude drawn to its hypotenuse, okay, it will create 3 similar triangles, okay? There'll be 3 similar triangles in this situation here, okay? So the original triangle itself, okay, the original triangle, see 3 similar triangles total. So the answer is just right here. The original triangle itself is similar to the other 2 triangles that get created, okay? We proved that because of AA, right? We proved that because of AA. So triangle DNF, let's see if I can maybe type in here. My computer's being very slow. So angle D is congruent to angle D. So DNF is this big triangle here, but angle D is also congruent to angle D by reflexivity in this smallest triangle. We'll call this the largest triangle. Remember this? The largest triangle, the smallest triangle, and then kind of the second largest triangle, or the medium triangle, right? We call it the medium triangle here. So triangle DNF is similar to triangle D. Well, this is here. Remember, you have to get the corresponding angles to line up here. D and D is easy. It's the same angle in the largest triangle as it is in the smallest triangle. Angle D is the same freaking triangle, same freaking angle. So they correspond, they're congruent. N here in DNF is the right angle. Okay, right, look at this is angle N in DNF, okay? Angle DNF right here. So that corresponds to DEN, angle DEN in triangle DEN. And there you go, you have your answer right here, DEN up here, okay? So that goes to prove you that this angle's gotta be the same as angle F, right, okay? Through similarity, right? But anyways, we would know that that angle is the same as that angle because angle D measures the same as angle D. This is a 90-degree angle right here that measures the same as this one right here. So whatever's left over from angle D and then this angle here would be angle F. Whatever's left over from angle D and this angle here would also be the same thing, right? Same thing here. So F and N, right? F here in the large triangle versus N in the smallest triangle, they correspond here. So that's how it gets written down. DNF here, next one. DNF is similar to, well, the medium triangle as well. So F is going to line up here. So I know I'm going to have F at the end of this, okay, at the end of that here. And then we're going to have N, which is, again, the right angle here is going to be E, okay, E in this one. And finally, n, right? Got it by process of elimination here, that E is the right angle in the medium triangle. That's gonna, and N is the right angle in the large triangle. Okay, and it all matches up, and we got it lined up here. And then just by knowing how to write this out conveys that information to us about which angles correspond, which angles got to be congruent through definition of similarity, right? If we use it later. Okay, number 5. Here's the geometric mean tattoo. Here we go. So we put it to use. All right, here we go. NE is the geometric mean. So this is sort of testing. Do you remember this theorem here? Well, this is the altitude drawn to the hypotenuse of a right triangle. Oh, do you recall these theorems? I'm not going to read through them because I know them here. All right, the altitude to just this is it. You just got to remember this. You gotta get note cards, right? Note cards going. So you can relive the logic of it. We use logic to arrive at things we can kind of memorize, so that we can apply them. We can solve problems very quickly, right? There's no reason to logic through the same exact thing again and again and again about why and is the geometric mean between certain figures. Some of these things you just got to memorize, okay? So logic, very important. Understanding how things work, super important. But being able to realize, hey, this has got to be a fact, so let's just memorize this fact. That is an important skill too, which maybe it hasn't been emphasized too much in your experience here. It's like not thinking through why this is the case all the time. Because you think through a why a few times, and then you accept that it's true, memorize it. Because then you can just use that fact, okay? NE, okay, that's why I want you memorizing this fact, right? This goes on a note card in case you forget this stuff here. The length of the altitudes, that's the altitude of the hypotenuse of a right triangle. It's the geometric mean between what? Well, DE and EF, okay? Check it out here. DE is smaller than NE. EF, larger than NE. So NE, right, that kind of makes sense. That this is kind of a mean of some kinds, right? Mean, remember, means average, okay? This is smaller, this is larger. This kind of looks like it's probably like an average, geometrically, okay? Well, DE, that's the smaller side of the smallest triangle. NE is the smaller side of the medium triangle. So they actually correspond. That's why that happens. So remember, NE is also the larger leg, right? Larger leg of this small triangle. And it is also the this here, larger leg of this. And it's the smallest leg of this one. Let's see, wait, it's a small leg here and a small leg in the right one. And yeah, it's the small leg here. Oh, wait, and then larger leg. Sorry, yeah, it's a larger leg of the left one and larger leg of the right one. Here's where you just need to memorize it. Be helpful here. So that's the reason why it works, right? Smaller leg in the DE is DE. This is the smaller leg in this right triangle, this right side triangle, medium triangle. This is the larger leg in the left triangle. Well, EF is the larger leg. So DE and EF, like they have this proportionality kind of type of thing here. Okay, so NE is the geometric mean between DE, okay, DE and EF. There you go. So we have to know that one and apply that one. Use that to solve problems here, okay? NF, okay, so the NF looks like that's a leg of the right triangle. So remember, it's all up here. It's all up here. This is it. As it all relates to hypotenuse, okay? NF is the geometric mean between the segment of the hypotenuse it's adjacent to, so that's EF, and the whole hypotenuse itself, which is DE. And there's your answer right there. So I got EF and DE. That's my answer here. Okay, if DE equals 10, okay, if DE equals 10 and EF equals 15, then ND, ooh, interesting. Okay, this is where you can get tricked. You can get tricked pretty quickly. So it's asking about ND. Remember, ND, and I might just type in here, our equation for ND is this. ND is the geometric mean between the segment of the hypotenuse, that's DE. They're talking about DE up there. Okay, there you go. ND is there. And then we have, okay, ND is the geometric mean between the segment of the hypotenuse it's adjacent to and the whole hypotenuse itself. So that's DF right here. So we got this here, ND. We'll put in the mean positions. In the extreme positions, we have DE, this segment of the hypotenuse, and then DF, the whole hypotenuse itself. Did they talk about DF here? No, they didn't. They're trying to trick you, my friends. Trying to trick you. So remember, DE, definitely shorter than ND right here. Look, it's definitely shorter than it. DF, way bigger. Okay, so you average DE and DF in terms of a geometric mean average, you get ND right here. Okay, so that they're trying to trick you out here because ND looks like it actually might be bigger than EF. Like, see, I mentioned AF right here. That's what they want you to do. My mistake is just, well, I see two numbers. Let me get the geometric mean of them. No, slow down, slow down. Are they trying to trick you, right? In this one, they are trying to trick you. So ND it might be bigger than EF. It's definitely bigger than DE. If it's bigger than both of those, it's not a mean. It's not a mean here, okay? So that's one way that you can not get drawn into a trap like that here, okay? So check it out. We have this. So how would you do this? Well, you have to use the segment addition postulate, right? This is the segment of the hypotenuse here. This is the other segment of the hypotenuse, and the whole hypotenuse equals the sum of them. So 10 plus 15 is 25. So, right, what we just got to do is ND equals the geometric mean. Okay, open keypad, that's how we get a square root symbol here. Hit that button. We do square root symbol, and we're going to do 10 times by 25. Okay, 10 times by 25, and that's 250. Okay, so square root of 250, can you actually, can you reduce that? You can. Okay, and then you're going to get this, because 25, right? 25 goes into 250, and square root of 25 is 5, right? It's 5 right there. So 5 root 10 would be your answer, right? Because 25 times 10 is 250. So 5 root 10 is our answer right there. 5 root 10 is our answer, and we got it. We're good to go on that one, okay? 5 root 10, and I might have to copy this, move it up top so you see it here. Okay, and there we go. Okay, so we got that. Very good. Okay, let's check it out. Next one. And this, okay, what kind of a triangle here? Okay, well here, this thing, be very careful with this one. If a triangle can't be formed, right, not possible. So remember, there's the triangle inequality theorem, which I remind you of here, that if you have a larger side, then the two smaller sides still need to be larger, still need to be bigger. The sum of the two smaller sides needs to be larger than the largest side in order for a triangle to actually freaking get formed, okay? Because if you have a really long side and you have two tiny other sides, how would you have that one really long side and how would the other two sides ever really come together? They would just not. They were just too small. So anyways, this top one here jumps out to me because 8's pretty big. That's like larger. So 3 plus 4, right? 3 plus 4 is 7. That doesn't get us to an 8-sided thing, right? So 8 can't be a side because 3 plus 4, the other two sides aren't going to be able to intersect if they're at the ends of the 8 side here. They only have 7 in length in the sum here. So this one is not possible. Okay, so not possible for A. B is definitely going to be possible, right? 11 plus 12 is 23, and that's way larger than 13. We're good to go. But what is it? Okay, what is it here? Well, let's got to check this one out. All these, first of all, you can get these answers pretty quick because these numbers are actually pretty close to one another. So if they're pretty close to one another, they're pretty close to being equilateral. An equilateral triangle is like a bunch of 60-degree angles. It's very acute, right? Definitely all under 90. So check it out here. So this is the Pythagorean Theorem plus theorems, right, that we talked and proved here. But if the square of the largest side is greater than the square of the sum of the squares of the two smaller sides, then it's obtuse. If the square of the largest side is less than the sum of the squares of the smaller sides, then it's acute. Okay, so let's check it out here and see what it is here. I might do the largest side first to see what we're working with, like where that threshold is going to be. 13 squared, I can do that in my head. It's helpful to do in your head. You know, do squares of 1 through 15. If you memorize square root of 1 is square of 1 is 1, square of 2 is 4, square of 3 is 9, right? Go up, square root of 11 is 121. Square of 12, the square of 12 is 144. Square of 13 is 169. You just do things a lot faster. It should be able, okay? Square root of 169, so that's 169. 12 squared is 144, and I know 11 squared is 121, so that's way bigger, right? 121 plus 144, way bigger than 169. So this is going to be the sum of the squares of the two smaller sides. So the sum of the square. So it's helpful to kind of think about it. Remember, from the largest side's perspective, the square of the largest side is smaller than the sum of the squares of the two smaller sides. So that means it's going to be acute. Okay, going to be acute. It's closer to like kind of an equilateral triangle here. These are all close together. Okay, try this one out. 7 squared. What's that? 49. 7 squared, also 49. So the sum of the squares. So this a triangle can definitely get formed, right? Because 14, the two smaller sides added together exceeds. It's larger than the third side. So here we have 49. This is 49. That's added together. It's 98. 10 squared is 100. So the square of the largest side is larger than the sum of the squares of the two smaller sides. So this one's obtuse. Okay, this one's obtuse here. All right, again, I'm doing these kind of quickly and not showing them all out. Right, that's what the lessons were for earlier, and hopefully you're seeking out help if you were having trouble with this here earlier. Okay, check this one out here. Fractions. Ooh, fractions problem. Is this one going to be possible? Well, yeah. This would be 7/5 if we add them together, and that's larger than 1. That's like 1.4 or so. Okay, so now I'm going to square this. We'll square of 1 by square of 1. that's 1. If I square 3/5, remember that's 3/5 times 3/5. So I would get 9/25, okay? 4/5, if I square that, I get 16/25. 9 plus 16 is 25, so I get 25/25. So yeah, this one's going to be right. Okay, this one's going to be right. My guess is that, yeah, it kind of makes sense you'd have one right one. You're using the converse of the Pythagorean theorem, and that one's that one. I mean, you can show out the work, that might be helpful. But again, I think the emphasis in this would be shorter, so you can check your answers. Check in with me if you're having trouble. All right, solve for x. Hey, I think these are special right triangles problems, don't you think? Okay, 45, 45, 90. Like, check it out here. Got it all laid out for you. It's what we're practicing, right? Hopefully you remember it. Okay. Oh, I wrote that incorrect. That's incorrect right there, guys. That's a typo. That's totally a typo. That's absolutely a typo. It's 1 to 1 to root 2. That is the ratio here. 45, 45, 90 is a 1 to 1 to root 2 ratio, not 1 to 1 to root 3. That's wrong. Okay. So here for A, if you have a leg, right, the legs are going to be the same of a 45, 45, 90 degree right triangle. Interesting here that they never wrote the right. Oh, it's isosceles. Okay, yeah. 45, 45. So there's only, out of 180 degrees, this is 90 of it, so this has to be a 90 degree angle. So anyways, 45, 45, 90, special, it's half of the square, okay? So going from the small side, I'd have to multiply x by root 2 to get us to root 6. So then the way we go backward is we take root 6 and what do we divide it by? We divide it by root 2. So it turns out that the answer here is going to be root 3. Okay, root 3 times by root 2 is root 6. Remember, I wrote this wrong. This should be a 1 to 1 to root 2 ratio here. That's incorrect. So anyways, our answer here is root 3. Do I need to explain it more? I don't know. I feel like if I write you a message being like, you didn't get that one, you're going to be like, well, your explanation really helped me here. What is this here? Well, root 3 times by root 2, remember, if I multiply two roots together, then I just multiply what's inside the roots together. And 3 times 2 is 6. So if this here's root 3, the hypotenuse is root 2 times longer. There we go, right? Root 3 times root 2 is root 6. And that verifies my answer is correct. Okay, this one here, 30 degrees is going to show me where my smaller side is because the opposite's the smaller side. So here, when I do problems like this, my recommendation is always detour to the smallest side because remember the smallest side of a 30, 60, 90 is going to be, it's going to be a 1 to 2 ratio with the largest side here. Okay, this is root 3 times longer than this one. So what is this one here? This one's 7. Okay, this one's 7 here. B's got to be 14. Okay, B's got to be 14. Check it out. So I'll put the 14 in here. Okay, 14. That's my answer there. Okay, last one, this one right here. Ooh, I'm gonna have to do this elsewhere to type it out to make sure it works here. This just looks like a Pythagorean theorem problem. Okay, so here, what I'd have to do in this one, maybe I'll type it out for you guys here, is this: 7 squared plus x squared equals x plus 1 squared. The mistake I see people making on this one is their algebra 1. Okay, check it out here. X squared, so a squared plus b squared equals c squared. That's it, right? Leg squared, the sum of the squares of the legs of a right triangle equals the square of the length of the hypotenuse, okay? Don't be like the scarecrow. Get it right. Get it right here, okay? So x squared plus 7 squared, okay, that's 49, but maybe I'll show it to you later, is equal to x plus 1 squared, okay? Remember, x plus 1 squared is actually a little bit more confusing than what meets the eye, because remember, that's x plus 1 squared isn't x squared plus 1 squared, right? It's not that. It's not just x squared plus 1. We're actually going to add a square in there and then just have 1 squared here. That totally makes sense here. X plus 1 squared is the same as x plus 1 times by x plus 1. It's by the whole binomial right here, x plus 1 times itself, right? Times by x plus 1. So if you look at this here, if you studied FOIL in Algebra 1, F-O-I-L, first, outer, inner, last. You study that one at all? Or do you generic rectangles? Okay, my base is x plus 1. My height is x plus 1. I get those 4 terms in the middle. I got to multiply together. Anyways, x times x is x squared. Okay, x times x. So first, I'm doing FOIL here. I'm just showing you. FOIL means first. The first one. FOIL means you have 4 of these terms together. 2 of those terms have 2 of those terms. It's just a trick to how you distribute everything here. Well, I'm going to do my first terms. X times x is x squared. Now I'm going to do my outer terms. Those are the ones on the outside. X times 1 is just simply x. Okay? And now I'm doing my inner terms. 1 times x is simply x, right? Or 1x here. And finally, I'm going to do my last terms here. These are my last terms because last in both of the binomials. 1 times 1 is 1. So here, what people oftentimes forget, and that's the reason why this is a problem, this one, they forget to multiply 1 times x here and 1 times x here. Anyways, little algebra 1, I'm going fast because this is an algebra 1 here, okay? So this is me rewriting x plus 1 squared. So let me just change this here. I got x squared plus 49 on the left side of this equation. Okay, x squared plus 49, and that equals x squared plus 2x plus 1. Now I need to solve for x. Well, I have x squared on this right side of the equation, I have x squared on the left side of the equation. I can subtract x squared from both sides. Those go away. So 49 simply equals, right? Get rid of my x squareds there and take them away. 49 is going to equal 2x plus 1. And you should all be able to know how to solve that one, right? Don't you? Subtract 1 from both sides, you get 48 equal to 2x. 48 equals 2x. Well, what does 1 actually equal? I divide both sides by 2. I get 24. Okay, so x is 24 in this one. Hopefully that one's right. I don't know if I've done this problem set before. Okay, so I got 24 equaling x. Okay, so a little bit of maybe a sanity check that perhaps you did this group work thing correct here, because those are the answers. Okay, so I'll try to look at yours tomorrow as well and send you away. All right, send me a message if you have any questions. Start studying. Let's get on it. Right triangles. Quiz this Friday. Let me know if you need any help or want to come to office hours today. I'm willing to meet with you. Take care. Bye.